In the last couple of lectures, we've discussed diagonalizability in some depth. We found necessary and sufficient conditions for a matrix to be diagonalizable, both in terms of the subspace representation, that is in terms of the arithmetic and geometric multiplicities, but also in terms of the minimal polynomial and its relationship with the characteristic polynomial. Now, diagonal matrices are nice because they help us in many applications. In particular, if we want to say compute a large power of a matrix, for example, if you want to compute a to the n, and if a is diagonalizable as p d p inverse, then computing a to the n can be done efficiently by just computing p times d to the n times p inverse, and since d is a diagonal matrix, d to the n can be just done by powering the diagonal elements. Okay? But unfortunately, life is not good if the matrix is not diagonalizable. Okay? So what is the best that we can hope for? Can we still do something better than brute force computing a to the n? So it would be nice if the matrix were at least block diagonal. So for example, if we have So if we had A, which could be written as tiny blocks, A1, A2, up to say AK. So if the matrix were block diagonal, then A to the n could be computed by powering each block separately, right? So it's A1 to the n, A2 to the n, so on, AK to the n. So if our matrix were similar to a block diagonal matrix, then we could at least do something better than finding a to the n using the brute force approach, right? And that is precisely what the primary decomposition theorem can guarantee us. So we'll see that every matrix is similar to a block diagonal matrix, and we'll give a characterization of what these blocks correspond to. So before we get into that, let's quickly recap what we saw in the last lecture. Right? So we saw that if a vector space V, so in our case we're typically taking V to be R to the n. So if V can be written as a direct sum of V1 plus V2 plus so on up to Vk, then we can always find projection matrices EI. So EI is a projection from R to the n to the subspace Vi, the ith subspace Vi, such that these EIs satisfy the following nice properties. So the identity matrix or the identity transformation is equal to E1 plus E2 plus E3 up to Ek. So all the EIs sum together to give the identity matrix, and EI Ej equal to 0. So if I is not equal to j, right? So basically, if you project, so what property 1 is saying that is that if you take a vector and compute the sum of the projections into the various subspaces V1, V2 up to Vk, then you get back the vector itself. And what the second property is saying is that if you project onto the jth subspace and then you try to project that vector into the projected vector into the ith subspace, then you just end up with the 0 vector, right? So we'll extend this. So this is in general for any direct sum decomposition of V into V1, V2 up to Vk, and in this and we'll add an additional property to direct sum decompositions by requiring them to be sort of invariant to linear transformations. So given an arbitrary linear transformation T from V to V, we'll say that a subspace of V is T invariant if you take any vector from Vi, then if you take any vector from the subspace and then you transform it, then you come back to the subspace itself. So basically T cannot take any vector from this particular subspace to outside the subspace. So formally speaking, Vi, which is a subset of V, is said to be T invariant if for all so vi is t invariant if for all vectors in vi t times x is also in vi, right? And suppose that we have a direct sum decomposition of v into v1 plus v2 plus v3 up to vk, then and suppose that each vi is t invariant, then we call such a direct sum decomposition as a t invariant direct sum decomposition, right? And shortly we'll see why this notion of t invariant direct sum decomposition is, right? So let's first look at sort of the simplest example and one that we are all familiar with, right? So diagonalizability. Right? Suppose that a matrix is diagonalizable, and let's take the VI's. So if the matrix is diagonalizable, then basically we can form then a basis for V or basis for Rn is simply the set of eigenvectors, right? So we can form a basis purely of eigenvectors, and what we can do is we can write V as a direct sum of subspaces, in fact a direct sum of the eigenspaces of the matrix. So suppose that we have suppose that T has eigenvalues lambda 1, lambda 2 up to lambda k, and let v1 v2 up to vk be the eigenspaces corresponding to lambda 1, lambda 2 up to lambda k, then V can be written as a direct sum of these eigenspaces. And why can we do this? So firstly, notice that if you take, so if Vi is the eigenspace corresponding to lambda 1, and you take any vector V from Vi, right? So but T times V is equal to lambda 1 times V, which is also in Vi, right? So it's certainly, so each eigenspace is obviously T invariant, but it's also a direct sum decomposition because notice that we had a necessary and sufficient condition for a direct sum decomposition to be T invariant, in that if we could take basis B1, B2 up to Bk, and if all of these put together forms a basis for V, then it's a direct sum decomposition. And indeed that is the case, because we can choose B1, B2 up to Bk to be the eigenbasis for each eigenspace, right? And obviously, since T is diagonalizable, the collection of the basis vectors for B1, B2 up to Bk put together obviously span V and also forms a basis for V, right? So, but what is interesting about a general T invariant direct sum decomposition is that with respect to the basis corresponding to these subspaces, the matrix corresponding to T has a very nice structure. So let us suppose that V can be written as a direct sum of V1, V2 up to Vk, right? And let's look at basis vectors for V1, V2 up to Vk, right? Let's suppose that V11 up to V1I1 is the basis corresponding to V1, right? So the dimension of V1 is I1 and the dimension of V2 is I2. So let's suppose that V21, V22 up to V2I2 forms a basis for V2 and so on. Right? So this obviously gives a vector space, it gives a basis for V, and with respect to this basis, what can you say about the matrix of corresponding to T, right? So relative to this particular basis, what could the matrix look like? Now remember that since these subspaces are all T invariant. If you take any vector from Vi and you apply T on that particular vector, then you end up in Vi itself, right, in the subspace Vi, right? So with respect to this particular basis which I have described here, what do you think the matrix form of T would be? I want you to pause the video and think about this. All right. So note that if you look at Ti, if you look at T, then relative to this particular basis, the matrix form would simply be a block diagonal matrix. So it would have the form T1, T2 up to Tk, where Ti is simply the restriction of T to the subspace Vi. And why is that? Because when you represent in terms of this particular basis, you know that if you take say a vector v21, you know that T times v21 is going to be in the subspace calligraphic v2, and therefore T times v21 can be written as only as a linear combination of v21, v22 up to v2i2. Therefore, corresponding to v21, corresponding to this particular subspace, you have a block diagonal matrix. Similarly, corresponding to calligraphic v1, we have a block diagonal matrix T1, and so on, right? And recall that our goal is to somehow convert any given matrix into a block diagonal matrix. So if we have a T invariant direct sum decomposition of V, then effectively we have found our block diagonal representation, right? So as an example, here's an almost trivial one. Suppose that T is block diagonal, right? So if T has this particular form 1 2 0 3 4 0 0 0 1, then what are V1 what are script v1 and script v2? So script v1 is simply the xy plane, and script v2 is the z-axis, right? Because if you take any vector which is in the xy plane and apply t, then you get back another vector in the xy plane. Similarly, if you take a vector in along the z-axis and you multiply this by t, then you get back another vector along the z-axis, right? And it's also obviously v1 v1o plus v2 gives you v, which is r3, right? So obviously in trying to find a block diagonal representation of a matrix, we have to find a T invariant direct sum decomposition. The two are obviously interconnected, right? So the question is, when is a direct sum decomposition T invariant, right? Suppose that we have a direct sum decomposition of V into V1, V2 up to Vk, then are there, what necessary and sufficient conditions can we give for this decomposition to be T invariant? Because obviously not all direct sum decompositions are T invariant. In the previous example over here, if I obviously R3 can also be written as V1 prime plus V2 prime, where V1 prime is, say, the xz plane and V2 prime is the y axis, right? Because if I take any vector along the y axis and apply t, then I get something in the xy plane, right? In general, so I can't really, although this is a valid direct sum decomposition of R3, this is not T invariant for this particular T, right? So when can we say that a direct sum decomposition is T invariant? Now if we look at the projection matrices corresponding to each of the VI's, so since we have this direct sum decomposition v into v1 plus v2 plus all the way up to vk, we also have the corresponding projections e1, e2 up to ek, where ei projects onto vi, and we also have the property that ei ej equal to 0 for I not equal to j, and the sum of the ei's is equal to the identity matrix, right? So we have this collection of projection matrices, and a necessary and sufficient condition for this direct sum decomposition to be T invariant is that T times ei should be equal to ei times T for all I, right? So in other words, the projection matrices should commute with the operator T. Okay, and anyway, I mean, you can look at this previous example and see that this is indeed true. So for example, you can take E1 to be this matrix over here, so it's a projection onto the xy plane, and E2 to be this matrix, which is projection along the z-axis, right? And you can easily verify that T times E1 is equal to E1 times T, and T times E2 equal to E2 times T. All right. So a direct sum decomposition is T invariant if and only if T times ei equal to ei times T for all I. Now let's try to prove this, right? So let's do it step by step. So it's an if and only if condition. So we have effectively two statements to prove. So let us start with the assumption that the direct sum decomposition, so let us assume that T times ei is equal to ei times T. Okay, let's say that TEI equal to ei times T for all I, right? So and what we want to prove, we want to prove that T is so each vi is T invariant. So basically, if alpha belongs to vi, then T times alpha is also in vi, right? So this is what we want to prove. This is what we know. This is what we want to prove, right? So let's take any alpha in vi, right? So what does that mean? What do we know about alpha over here? We know that since alpha is in vi and ei is a projection matrix, alpha is in the range of ei, therefore ei times alpha is equal to alpha, right? So that's a very important property that we'll use. So if we take T times alpha, then this is T times ei alpha, right, which is TEI of alpha, but we know that TEI equal to EIT, so this is EI T alpha, right? But what is the range of EI, right? EI, the range of EI is VI because it's a projection matrix, right? So EIT alpha is in VI, right? And so T alpha is in VI for every alpha in VI. In other words, each script VI, each subspace VI is T invariant. Okay, so we've done one part of the proof. So now let us assume that each EI is T invariant, right? And now we want to show that T EI equal to EI times T. Okay, so let us consider any vector alpha, right? So any vector alpha in Rn, which is V, right? Now note that we can always write alpha as I times alpha, which is E1 plus E2 so on plus EK times alpha, because of the nice property that the EI, that the projection matrices have, right? So let's consider this. Now if I look at T times alpha, this is TE1 alpha plus TE2 alpha and so on, TEK alpha. Okay, so this holds for any arbitrary alpha in the vector space, right? But what do we know? We know that T is each of the subspaces is T invariant, and in particular, so E1 alpha is in V1, so this is in V1, this is in V2, and this is in Vk, right? But since each of these subspaces is T invariant, T times E1 alpha should give you another vector in V1, T times E2 alpha should give you another vector in V2, and so on. So I can write this as beta 1 plus beta 2 so on up to beta k, right? That's true, right? But anyway, so let me not even do that. Just why introduce unnecessary notation, right? So each T E1 alpha is in Vi, so each T EI alpha is in Vi, right? So this TE1 alpha is in V1, TE2 alpha is in V2, and so on. Okay, so now for any j, take EJ T alpha, right? So this is EJ TE1 alpha, EJ TE2 alpha, and so on, right? But we know that this lies in V1, this lies in V2, and so on, and EJ is a projection matrix, right? And so we know that if we take any vector in so if we take any vector from Vi and multiply it by Ej x, this will be equal to 0 if j is not equal to I, right? So Ej times TE1 alpha will be equal to 0 if j is not equal to 1, right? So all of these get killed except Ej alpha, right? So this is equal to Ej alpha, but since this is already in Vj, Ej times this is equal to the vector itself, right? So this is Tej alpha, right? Because if I call, so let's suppose that I call this beta 1, beta 2, and so on all the way up to beta k, then Ej beta I equal to 0 if I is not equal to j, and Ej beta j equal to beta j, right? And beta j is simply tej alpha, right? So effectively what we proved is that for all j and for all alpha in V, ej t alpha is equal to t ej alpha, right? And obviously this implies that ejt equal to tej, since this holds for all vectors in the vector space. Okay, so finally we've proved that a direct sum decomposition is T invariant if and only if TEI equal to EIT for all I. Right? So what does this imply for a diagonalizability? It implies that if lambda 1, lambda 2 up to lambda k are distinct eigenvalues of T, and the corresponding eigenspaces are V1, V2 up to Vk, the corresponding projection matrices are E1, E2 up to Ek, where these EIs, okay, so if they are the corresponding projection matrices, then we have the following properties. So firstly, T can be written as lambda 1 E1 plus lambda 2 E2 plus all the way up to lambda k Ek, because if you look at any vector V, then T times V can be written as T times E1V plus E2V and so on up to EKV, but EIV lies in the in the first in the ith eigenspace, and therefore T times EIV equal to lambda I times V. So this is lambda 1 times E1V plus lambda 2 times E2V and so on, lambda k times EKV, right? And by the special properties of these projection matrices, the identity matrix is equal to E1 plus E2 up to Ek. EI Ej equal to 0 if I not equal to j, and since EI is a projection matrix, EI squared equal to EI. Right? So this holds for any diagonalizable matrix T. So obviously what happens with non-diagonalizability, and in particular, so note that in all our discussions on diagonalizability and diagonal matrices so far, we've implicitly assumed that the vector space is Cn, and the reason is because if the matrix has complex eigenvalues, then we haven't really seen how to handle it, because obviously if lambda I is complex, then lambda I times, then you can't really say that T times V equal to lambda I times V if you are dealing with Rn, right? So in particular, if the vector space is R2, and let us suppose that we have a matrix whose characteristic polynomial is say x square plus 1, then this is not really diagonalizable over R2, right? Because we know that it is diagonalizable over C2, the field of complex numbers, because the eigenvalues are plus I and minus I, but it is not really diagonalizable over R. In particular, you can try the following. So suppose that, let's take a matrix which has this characteristic polynomial. Let's see. So I guess this should do it, right? So if we take A to be equal to 0, minus 1, 1, 0, then lambda I minus A is lambda 1 minus 1 lambda, and therefore the characteristic polynomial is going to be lambda square plus 1, right? And I encourage you to actually prove that over Rn you cannot diagonalize this particular matrix A. So in particular, if you cannot find a non-zero vector x such that 0, -1, 1, 0 times x1, x2 equal to alpha times x1, x2 for a non-zero value alpha. Right? Okay. So in such scenarios, what can we do? Can we if the matrix has complex eigenvalues, then is it block diagonalizable, and if so, how? Right? And all of these questions are answered by the primary decomposition theorem. It says that for any linear transformation T, we can always decompose V as a direct sum of T invariant subspaces V1, V2 up to Vk, and these subspaces are going to be the null space of certain matrix polynomials. And what are the matrix polynomials? So if the minimal polynomial is p of x, which is p1 of x to the r1 times p2 of x to the r2 and so on up to plx to the rl, where each pi of x is an irreducible polynomial, which means that you cannot decompose over that particular field, you cannot decompose it into a product of polynomials of smaller degrees, then vi is equal to the null space of pi of a to the ri. So to take a very simple example, let's maybe consider a to be 0, -1, 1, 0, 1, 0, 0. So lambda I minus a would be equal to lambda 1, 0, -1, 0, -1, lambda 0, 0, 0, lambda -1. Right, and this and the characteristic polynomial is determinant of lambda I minus a, which is lambda -1 times lambda squared plus 1, right? And I encourage you to verify that this is indeed the minimal polynomial of this particular matrix A. Right, so obviously it's an annihilating polynomial. Now it turns out that we can write this as a direct sum of two subspaces, V1 and V2, where V1 is the null space of A minus I and V2 is the null space of A square plus I. Note that this matrix is not diagonalizable over R if you view this as a transformation from R3 to R3. It is, however, diagonalizable if you view this as a transformation from C3 to C3. So in the next lecture, we'll see a couple of small examples and maybe give a sketch of the proof of the primary decomposition theorem.